Welcome to those who are attending this year's Thermal and Fluids Engineering Conference. My name is Klinkhamer and I am a PhD student in the Department of Mechanical, Automotive and Materials Engineering at the University of Windsor in Ontario, Canada. I will be presenting our full paper titled The Effects of Standoff Distance and Jet-to-Jet Spacing on the Heat Transfer Performance of an Inline Array of Submerged Impinging Jets. On behalf of our research team, I'd like to first acknowledge the co-authors of this work, Dr. Abhishek Sridhar, Dr. Rambala Chander, Dr. Ronald Barron, and Dr. Lashimi Iyer. Throughout multiple decades, jet impingement had been extensively adapted towards applications that require high heat and mass transfer, and this is due to the high heat transfer coefficients that can be obtained within the stagnation region of the jet and the great turbulence intensities that are realized within the wall jet regions. We look to study the available correlations that are commonly used in the literature, such as those for single jet impingement or square and staggered arrays of impinging jets, and we look to investigate the applicability of these correlations towards the inline array type. Furthermore, we look to develop our own new correlation that can effectively predict the heat transfer performance of the inline array type in terms of the Nusselt number. The figure shows the general flow field in which we are studying, where the high velocity jets are equally spaced and are within the same vertical plane, hence they can be considered to be inline jets. The right figure shows a general schematic of a jet impinging onto a heated surface, and the left figure illustrates a schematic of the different array types. One parameter of interest is the standoff distance, which is denoted by h. This h is typically non-dimensionalized by the jet diameter d. Likewise, the jet-to-jet spacing, represented by s, is typically non-dimensionalized by the jet diameter as well. And this is another critical parameter that is used in the development of the correlation. We can see by the dashed red lines a cell area which is clearly defined for the square and staggered array types. Many of the correlations for these array types define a relative nozzle area defined by equation 1, which is the jet area to cell area ratio. Moreover, it is important to note three distinct regions of the free jet: the stagnation region, the free jet region, and the wall jet regions. In the free jet region, the jet is expelled into the stagnant ambient fluid, forming an annular shear layer, which helps aid in the entrainment effect, which is the entrainment of surrounding fluid, which effectively increases the jet's mass and reduces its velocity. The jet will then reach the stagnation region, where it is gradually brought to rest, and it is here where the highest heat transfer coefficients are achieved. The jet will then expand radially outwards, forming the wall jet region, and it is here where secondary peaks in the heat transfer coefficients can be achieved, typically due to acceleration of the wall jet, or due to the wall jet's transition from laminar to turbulent. The extensive literature shows that more recently, jets have become an attractive solution for power electronics cooling, and this was demonstrated in the works of Jorg et al., as well as in the works of Naromanchi, which showed the benefits of jet impingement over a baseline channel flow. The early works of Bon and Shimizu, as well as the works of Hoffman, outlined the effects of h by d on the heat transfer performance. Shademan also looked at large h by d effects and highlighted the secondary Nusselt number peaks that were also noted by Bon and Shimizu at small values of h by d. This was contributed due to peaks in the wall shear stress at small values of h by d, such as 2. For arrays, Obot and Troubold studied crossflow effects, which, if at high intensities, reduced heat transfer. Moreover, Babani and Goldstein investigated s by d effects of arrays, which, if was less than 4, tended to cause increase in the mixing of wall jets, therefore reducing heat transfer. Here is a brief list of some correlations available in the literature, ranging from single jets to arrays of square and staggered forms. All jets here considered are round nozzles. Some of these correlations account for the jet-to-jet spacing by the s by d raised to some power, or by using the area cell size, or by using the relative nozzle area, which is denoted by f. A schematic of the experimental setup is shown. The working fluid is stored in an isothermal bath and is issued via a control valve which also controls the flow rate and is measured by a magnetic inductive flow meter. A filter is used to remove any impurities in the fluid and to prevent any clogging in the jet nozzles. Inlet and outlet valves permit the flow of fluid through the test rig. An additional vacuum pump pipeline attaches to a vacuum pump which removes air from the test rig prior to testing. Inlet and outlet temperatures are measured by K-type thermocouples, and K-type thermocouples are also used to measure the impingement surface temperatures. Pressure at the inlet and outlet is measured by pressure sensors, with the difference being reported by a differential pressure transmitter. This study investigated H by D and S by D in the range of 2 to 8 and 6 to 18.5 respectively. However, only experiments were done on H by D of 5 and S by D of 18.5 for the numerical model validation. Since it is not possible to directly connect a thermocouple to the impingement surface, cartridge heaters were installed into heater blocks, which were perfectly insulated with glass wool insulation and PEEK plastic insulation. Since the heater block is perfectly insulated, the heat transfer along the length of the heater block is one-dimensional. Therefore, by measuring temperatures at 3 locations from the impingement surface, we can effectively extrapolate the surface temperature by a linear relationship fitted to the temperature data. Furthermore, from this linear plot, dt by dx can be obtained, and therefore we can use equation 2 to predict the heat flow throughout the heater block, which is used as an input to our numerical model. The governing equations after Reynolds decompositioning are shown from equations 3 to 5, which are the Reynolds to average Navier-Stokes equations. Here we have the continuity equation or mass conservation in equation 3, followed by the momentum equation in equation 4, and then to fully define the heat transfer problem, we require the energy equation in equation 5. The system of equations is solved with our computational model, which is steady, incompressible, and 3-dimensional, with the entire testing rig being modeled. For turbulence modeling, the realizable K epsilon and K omega SST models employing an all Y plus wall treatment were compared. All fluid properties were determined at the bulk fluid temperature, and all solid properties were held constant. Furthermore, a uniform heat flux that was determined from the linear fit was applied to the top surfaces of each heater, and velocity inlet and pressure outlets were also used. The hexahedral mesh consisted of around 12 million cells in total, and this was the final grid. The mesh was refined particularly within the nozzles to capture large pressure gradients and within the impingement surface to capture large velocity gradients, as well as to capture the full characteristics of the wall jet region. Heat transfer, represented by the Nusselt number divided by the Prandtl number to the power of 0.42, is plotted with respect to Reynolds number for heater blocks 1, 2, 3, and 4. Here the Nusselt number is defined by equation 6, where Q double dash is the heat flux, D represents the jet diameter, Kf represents the fluid thermal conductivity, Ts is the surface temperature at the impingement surface, and Tb represents the bulk fluid temperature. As can be seen, both turbulence models with either the fine and the coarse grids provided both good matching with the experiments. Differences in the results are mainly contributed due to the inability to measure the complete temperature distribution over the impingement surface with only thermocouples. Based on the CFD results, the proposed correlation is shown in equation 7, and this is applicable for S by D in the range of 6 to 18.5 and H by D in the range of 2 to 8 and Reynolds number in the range of 3300 to 10,600. From this, it is possible in the early design stages to estimate the heat transfer performance of the array by only knowing the fluid properties, geometrical parameters, and the flow rate, or hence the Reynolds number of the flow. When compared to available correlations, equation 7 provides good agreement with predicting the Nusselt number at small values of H by D. At large values of H by D, when there is more opportunity for jet-to-jet interactions to occur, equation 7 deviates from those of Miola and Martin, which are based on hexagonal and square arrays, but shows good agreement with Lee et al. At all values of h by d. This indicates over the range of h by d and s by d tested, the jet-to-jet interactions are not significant, and each individual jet is not impacted by the other. Furthermore, the results suggest that the correlations of the square and staggered array types can't be applied directly to the inline array, particularly at large values of h by d. To conclude, we investigated h by d and s by d effects on the heat transfer performance of the inline array of impinging jets. From this work, a correlation was developed to predict the Nusselt number based on the Prandtl number, Reynolds number, h by d, and s by d, and this is applicable for s by d in the range of 6 to 18.5, h by d in the range of 2 to 8, and Reynolds number in the range of 3,300 to 10,600. The correlation provides similar Nusselt number predictions as the single jet impingement correlations of Lee et al., indicating weak jet-to-jet interactions in the range tested. The correlation tended to deviate from Martin and Miola at large h by d, when jet-to-jet interactions become more dominant. Hence, the present correlation can be applied to the inline array at small values of h by d, but tend to compromise accuracy at large values of h by d. To end, we would like to acknowledge the following, without which this research would not be possible. Magna International, the MITAX Accelerate Program, and the Center for Hybrid Automotive Research in Green Energy, and Dr. Narayan Kar and the Department of Electrical Computer Engineering at the University of Windsor.